If we want to perform a quantum gate in real life, because we want to manipulate its state, we can perform Robbie oscillations. Robbie oscillations are fast oscillations between states in a two-level system, for instance the 0 and 1 state. The oscillations are induced by electromagnetic radiation. The two-level system couples with the photons in the electromagnetic field, and if the frequency of the photons exactly matches the transition energy, the state will oscillate between the 1 and the 0 state. For instance, if we want to perform an X gate to flip the qubit from the 0 to the 1 state, we should apply an electromagnetic pulse of exactly half a Robbie wavelength. In other words, a pi pulse. On the Bloch sphere, Robbie oscillations can be seen as rotations around the x or y axis, dependent on the phase of the applied field. The Robbie oscillations do not fully reach the ends of the two-level system if the photon frequency does not exactly match the transition frequency. Then there is some finite detuning, a frequency difference. When you want to perform a qubit transitions with Robbie oscillations, this detuning is always present due to the quantum uncertainty principle. Nowadays, most qubits are still quite short-lived state, with lifetimes in the order of microseconds. Then Heisenberg's uncertainty principle tells us that delta E, which is the uncertainty in energy, times delta T, which is the qubit lifetime, should be bigger than the Planck constant. For short-lived states, delta T is small, so their uncertainty in energy, delta E, is quite large. And that is the reason why we will always have some random detuning, so an energy mismatch, when we perform Robbie oscillations on a short-lived qubit. This results in exponentially decaying Robbie oscillations. So the state vector doesn't reach the north and the south pole of the Bloch sphere anymore. If the decay of the Robbie oscillations reaches the 1 over E point, we have reached the decay time T Robbie, which is a measure of the qubit lifetime. There are multiple processes that could influence the lifetime of a qubit. The longitudinal relaxation processes, of which the timescale we denote with T1, and the transversal decoherence processes, which we denote with T2. Now for the decoherence processes, what we observe is always a combination of both static inhomogeneities from the environment, which we call T2', and transverse spin dephasing, T2. And then the aggregate of these two is called T2 star. And it satisfies the relation 1 over T2 star equals 1 over T2 plus 1 over T2'. In order to measure T2 independently of T2 star, we can perform a Hahn echo. Because the static dephasing of the environment T2' is time invariant, we can reverse the process by rotating the spins. The Hahn echo measurement sequence starts with a pi over 2 pulse around the x-axis to bring the state to the xy plane. Then, during a wait time t, the spin dephases in the xy plane, so its phase uncertainty increases. This dephasing is mainly dominated by T2'. Then a pi pulse is performed, so the spins will be rotated to the other half of the Bloch sphere. The T2' dephasing continues at the same rate, refocusing the spin. After a wait time of exactly t again, the T2' effect has effectively been cancelled. Then a measurement is performed to measure the effect of T2 isolated from T2'. By increasing the wait time and performing many of these Hahn echoes, the exponentially decaying population has a decay constant T2. So T2 is the pure transverse spin relaxation time. We perform a Ramsey experiment to measure the aggregate effect, T2 star. By applying again a pi over 2 pulse, we bring the spin in the xy plane. After that, we wait to let the transverse spin precession happen. The spin rotates around the xy plane with the Larmor frequency. After a time t, we perform the same pi over 2 pulse. and perform a measurement in the z basis. If the wait time is very small, close to 0, the spin will end up in the 1 state. And if the wait time is exactly half a Larmor period, the spin will end up in the 0 state. The measurement will show oscillations of a function of wait time. The oscillations will decay due to dephasing effects of both T2 and T2 prime. So what we measure is the aggregate effect of these two, and we call that T2 star. T2 star is reached when the exponential decay reaches the 1/e point.